So this guy is everywhere. Actually, to be frank, I don't think much of electronics was developed in the time of Einstein. He did this thing more from a diffusion perspective rather than a um, electronics perspective. I'm not very much sure whether semiconductors were he had any idea regarding semiconductors like we have today. Those people are always ahead of their time. Anyways, so this relationship uh, can be found separately for holes and electrons. If we can find one, we can easily find the another one. Okay, it's very simple. So let us begin with electrons. Before I go further, did I tell you something called effective mass in the last lecture? Did I somewhere mention this thing?
Yes, sir.
So what we said that if we want to apply the laws of Newton on the charge carriers, then we have to consider instead of their true mass, or if you want to speak in terms of relativity, instead of the rest mass of the electron or hole, we would require to calculate use something called the effective mass, because the situation is not like that it is totally free inside. We say electron is free to conduct, that is true, but the ambience around the environment around it is not totally empty. There are atoms, there are ions. That is there is a potential which we called as the periodic potential. So in that situation, the behavior is something different. We don't want to complicate things. That's why we want to apply Newton's law. So we are using effective mass. That is sometimes given as me star. Hmm. It can be positive or negative. Negative effective mass is for uh, holes. Fine. So what we would be doing, drift and diffusion, we could see that they are interrelated, isn't it? We can connect the two. Why? Because both diffusion and mobility, not a drift, better to say mobility. So mobility, what was mobility? Anyone? What was mobility?
So movement of electrons within the.
How was the movement? What factors was it dependent on? What was the expression for mobility? Yeah, you're correct. It is related with the movement. It was the drift velocity per applied per unit strength of applied electric field. That is how much the particle would be drifted if I apply an electric field. So now you can understand when the electrons are drifted, obviously there would be collisions, isn't it? Take the example of the school recess hours when you are playing randomly, you are moving anywhere, you're running in the playground. Suddenly the bell rings and the teachers are coming towards you. So what will happen? You all will be drifted towards the classroom, and definitely there is a probability of collision, isn't it?
Yes, sir.
And the probability would increase with the increase of number of students. That is, electrons they are in large number, so definitely there would be collisions. Again, the same kind of collision would be there if there is diffusion. That is, if the density or the concentration of particles in one part of the room is higher compared to the other. So when this barrier will be lifted, what will happen? Particles from this way will be rushing towards this side. Hmm. Definitely here also there would be collision. So you can see both mobility, which is related to drift, and diffusion, both are related by a common thing called collisions, isn't it? Is it clear, everyone, what I'm trying to say?
Yes, sir.
So now scientists came up with the idea, then how can we relate between mobility and diffusion numerically? So that is the main gist of this relationship. Fine. So what would be we would be doing? We'll consider a, say let us, we are doing for electrons, let us take a n-type semiconductor. Fine. Let us take it in form of a bar. You can take it in any form. Still simplicity to consider and imagine. What type of impurities are here if it is n-type?
Electrons.
What type of impurity, not carriers? I mean, what type of dopant?
Pentavalent.
Pentavalent, right? So we have added pentavalent dopants. So it has pentavalent dopants. Fine. Now we are assuming that the concentration of these dopants is non-uniform here. That is not a difficult thing to imagine. It may happen that the concentration of the or the distribution of the donor impurities is non-uniform. See, whenever there is non-uniformity, there would be diffusion. Keep this thing in mind. Non-uniformity in concentration, that leads to diffusion, isn't it? Can you understand this thing?
Yes, sir. It will be
Where is,
randomness, so that's why.
yes, why?
So like because of randomness of movement.
No, random, because of randomness is always there. Random, because of randomness, no, that is not the only reason. I told last day that randomness or thermal agitation is not the only reason for diffusion. What is the reason? The disparity in the distribution. I
So
gave the
because of
example of
high
that.
concentration in one
Right.
particle.
I gave the example of the agarbatti. Suppose you have lighted an incense stick in one corner of the room, and the fragrance is, circulated all over the room, and you had the ceiling fan switched on. So what you're telling is, yeah, you maybe the current is affecting that, and definitely the particles have some randomness in the movement, but that is not the only reason for diffusion. Okay, the more important reason is the non-uniformity in concentration. Definitely there would be some probability for diffusion due to randomness if there is uniformity also, but we won't call that diffusion. Okay, so what will happen? Due to this non-uniformity, obviously electrons would be diffusing from the higher concentration to the lower concentration. Clear?
Yes, sir.
So suppose let us try to take this one as the x-axis, x direction, and suppose this side is more dense. Sorry, my video quality has gone bad. Maybe no, it's fine. This side is less dense, so electrons would be moving in this direction due to diffusion. Mind it, we haven't applied any electric field yet. We don't intend to apply anything. So if electrons are moving this way, what will happen? It will give rise to a what? To a electric field, isn't it? If electrons are moving this way, so the electric field is expected to go this way, isn't it? How are the field lines drawn? Field lines are Field
Yes,
lines give
sir.
the direction of the motion of a unit positive charge. So see this electric field that is developed, it is internal. We didn't apply any battery from outside. Okay. So what will happen due to this internally generated electric field? What do you expect?
Current to be
Very
good,
good.
sir.
So there would be a current corresponding to the electric field. This current is due to what? Due to the diffusion of electrons. Okay, we haven't applied anything from outside. So what we have? We have, due to the internally generated electric field, we have a current which is flowing in the direction opposite of the opposite of what? Opposite of the electron flow. That is, we can say that the
Okay.
direction where electron is moving, we can call that direction to be the direction of diffusion current. Okay, diffusion current and the current which we mean by voltage and resistance terms, they are different things. Okay, you have to keep this in mind. Whenever we say current, it's not always that current has to do something with something that will give us a shock. Okay, that is always not current. Current is what? It is the, it's a mannered flow of something, a flow in a manner in a particular discipline. Okay, we say water current, air current, isn't it? So here, what is this current? This way we have the diffusion current. Is it clear? Why electrons are moving this way? And this way we have what? We have the current
Current.
due to the internal electric field. Is it clear?
Yes, sir.
So see, we haven't applied anything from outside. So what we expect, that in the equilibrium position, these two things will balance each other, isn't it? Every system, if it is kept on its own, it will try to settle down to a equilibrium. So the equilibrium case, what we expect, these two currents to be equal. So, and see, corresponding to the current, we have what? We have a current density. So let me call this as this, and let me call this drift. Keep it in mind, whenever there is current flow due to an applied electric field or internal electric field, anything which is arising due to E in form of current, it has to do with drift. So can I say that in equilibrium case, these two things are equal? Can I say this?
Yes, sir. It should be true.
Because current is proportional to the or potential, current density is proportional to the current. And whenever we consider something called density, we are not worried about the dimensions of the thing, isn't it? So that is a more meaningful term. So what is the expression for diffusion current for electrons? Is dependent on the charge, diffusion coefficient, and the gradient, concentration gradient. And what is this thing? By Drude's law or kinetic theory, Drude's law of electron flow, E n is the concentration or the number density of holes, mobility, the applied electric field, which is in our case the, it's not always good to say applied electric field, it is the electric field that causes drift. So these two things are same. Is it clear, everyone? Girls, is it clear?
So what is N, sir?
N is the number of electrons per unit volume, electron density.
Yes, sir.
This relation for intrinsic it was n equals to p equals to ni, and for n type it was much greater than the number of holes, and there was a relation of law of mass action. Okay, all these three things are very important for numerical problems. Fine. So one thing that I can see here is something like this. Let it be like this. In the meantime, what I will do, I will try to draw analogy between the kinetic theory of ideal gas or gases with the free flowing, freely moving electron. Okay, before that I will derive something. For that I will require the force. So what is the force on electrons per unit volume due to the electric field? Let me try to find this thing. Mod of E. I want to see what force the electrons are experiencing in unit volume. Why it will experience force in the first place? Because of this thing, electric field. So let me call this force as F. And if you can recollect the definition of uh, electric field or electric field intensity, it was defined as the force on a unit positive charge, isn't it? Remember this thing?
Yes, sir.
Oh, forget positive negative, we are taking the modulus. So dimensionally, force is equals to the charge times the intensity of the electric field. But now here, what I've considered, electrons in unit volume. So how many electrons are there in unit volume? N. And what is the force on each electron? This. Okay. Here, this one. So it is N into E into capital E. So I can find the expression of capital E from equation 1. So you can see if I just transpose some things, so what I would get, capital E is nothing but dn upon n mu n times the concentration gradient. You can put this in a bracket so that things don't get mixed up. Clear this thing? I am getting this
Yes,
from
sir.
equation 1. Everyone try to deduce this thing with me in your copy. That's why I'm not using PowerPoint or anything else. Okay, I'm taking the time so that you can do it with me. Do it in the first place, it would be helpful. Okay, so I can see n's are getting cancelled. So this thing looks something like this. But see, force is something which sounds fancy, but how can we, get the idea of the force on electrons, isn't it? Isn't that a bit difficult task, a tedious task, and to some extent unnecessary task? Hmm. But what we can have, what things we know, what we can, know, and what we cannot know. Cannot know is not good to say, which is hard to know this thing. Force on electrons, that is a bit difficult. But see, one thing is very easy to know, to calculate, to determine, that is the temperature. Anyone can do that if we have a thermometer. So now our idea would be to relate, or to better to say, substitute this thing in terms of this. Is it clear?
How, sir?
Yeah, that is the good question. How? Yeah, we'll get it. Another thing is very hard to know this gradient accurately. Yes, so the question is that how can we know this? So to how can we do this? To do this thing, we have to draw some analogy. Analogy means you have to compare this situation with another situation which is very close to this one, but which is not exactly this one. Hmm. So what is that thing? We will call for the kinetic theory of gases. Now this thing is analogous with this case. Why? See, what were the assumptions in kinetic theory? That the particle are freely moving, so are electrons once they're, you know, in the conduction band, or once they're not the conduction band, yeah, once they're free from the bonds, then motion of the gas molecules are random. It can be in all possible directions. So is with the electrons. That the total volume of all the atoms, if we compress, is very very negligible compared to the total volume of the container. Here also you can see uh, the total collective volume of the electrons is very very small, isn't it? So what sometimes we say that the electrons form something called a classical electron gas. Okay, any doubt with this?
And so,
Obviously it's a very classical concept. We haven't called for any, quantum mechanics or relativistic things. So if we do it like this, an analogy is not always a very bad thing to do, even in science. Hmm. Therefore we can say the pressure due to this gas. Which gas I'm talking about? The electron gas. I can write the pressure as N K. This thing I can write from the uh, kinetic theory of gases, isn't it? N is the number density, number of molecules per unit volume. In our case, it is the number of electrons per unit volume. K is the Boltzmann constant, and T is what? The absolute room temperature. Room temperature in absolute scale. Clear this one?
yes, sir.
Now we can also derive force from it. Actually, what is this force? This force is uh, not any force. It is the force per unit volume. Why? Because here we wanted to calculate that. So what is the dimension of force? Force is what? Pressure by area. Okay.
Yes, sir.
Fine. So can I write this thing as dpdx?
So like dx is the area, sir, per unit volume.
No, no, no. Dx is the dimension of length. Dx is not area. See, from here what I am getting, dp equals to f dx, where f is the force per unit volume. Is this expression correct or wrong? First tell me this thing.
That's correct, sir.
Everyone, is it correct? Is it correct? Yes.
I think so. Yes, sir.
So where did A go to?
No, no. Yeah. Is this thing correct? Is force equals to pressure by area or something else?
Yes.
So I think it's
No.
pressure is force upon area.
Then
Yes, sir. Yes, sir.
don't believe anyone blindly, especially during the election days. Okay. So pressure is force by area. That's why there is this confusion. Why this thing is happening? So pressure is force by area. And now this force is what? Force by unit volume. So dimensionally, this is pressure. This is not force. It is force by volume. Volume has the dimension of what? Cube of length. And this thing has the dimension of what? Length. So it's nothing but force by L square. I think it should be. That is force by area. Clear, everyone? Why this thing is happening like this? Why is it equal to this? Clear, everyone?
So in the right hand side, so yeah, replace in that differential form, sir, the dimension.
This one? No, 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 not. Oh, yeah, only the, yeah. I'm taking the unit. Dx, forget whether it is differential or integral. Dx means what? What is its dimension? Length.
Yes,
And
sir.
dp is what? It's pressure at the end of the day. So be very careful with this kind of mistakes. Fine. Okay. So what is p now? If I put the value of p, it is nkt. And you can see kt is constant and it is dn dx. So that is what we are getting force. Let me write this equation 2. So this would be equation 3. I'm taking time to deduce this thing because this kind of problems are very much commonplace in competitive exams. These derivation things. Hmm. Not the entire derivation, some portions. So by comparing these two equations, 1 and 3, I hope you all are okay now with the fact that I can assume this electron to be a classical gas.
Yes, sir.
That under that condition only we can compare these two things. So see, force has been replaced by this thing. See what I said, this thing is also something which is a bit difficult to be determined accurately. So we have got rid of that as well. So this is the relation. This is the Einstein's relation for electrons. So what you can see, the ratio of diffusion coefficient to mobility is equals to kT by E. Now If T is taken to be the room temperature 300 Kelvin, then we can calculate the value of KT by E also. If we put all the uh, values, can anyone tell me what is this value equal to?
So
So,
how much is this? So
right,
1.3.
I said it's
Yes.
1.3. So, like we can't see it properly, sir. It's coming blurry, sir.
Oh, acha, acha. It's
Oh, it seems.
Boltzmann constant 1.37.
Okay.
Sorry,
Like
it
it was
should be
coming
the
blurry,
unit.
sir, for a minute.
The unit would be volt, not joule. Sorry.
So which one is the equation 2, sir? Can you show me equation number 2, sir?
Equation 2, this one.
Okay, sir.
Calculate. I'm getting something like this 0.0256 volt. So if I multiply this by 1000, I would get things in terms of millivolt.
Yes, sir, got it.
So this is nearly 26 millivolt. It's a very important quantity. This quantity is called the volt equivalent of temperature. That is, what is the equivalent voltage value of the room temperature?
It's coming 0.024, something like that, sir.
0.24. It should come around it's around 26. I mean 0.026 something.
Yes, sir, 0.26, sir. Around 26.
Should come around 26. So you can have the similar this kind of relationship with holes as well. So similarly, with all the method we followed, we can repeat it. So for holes, we can get by so the same for holes. So you can see from here we can conclude this thing that dn by mu n is equals to dp by mu p, and which is a constant, isn't it? Sorry, it should be E. Holes have the same charge magnitude. Clear?
So that's volt equivalent temperature, sir.
Volt equivalent of temperature. Volt equivalent of temperature. This result is very important. We will be using it when we will calculate the barrier potential things. Is it okay, everyone?
Yes, sir.
Fine. So now this was actually the sub topic of the day, the main topic that is not that lengthy. So what happens when depletion region, potential barrier, whatever you'd like to think. So what happens if a p-type and n-type semiconductor are joined? Okay, what will happen? So before that, it is also important to know how this will happen. I mean, how can I join two p and n-type things? So the main thing that comes to the mind that I would, it's like suppose I have a bar of Cadbury 5 star, say it is p type, and I have Snickers, say it is n type. I just buy these two bars from the market. What I will do, I can build this portion and I'll join this, isn't it? That is what comes to the mind. So I'll have what? I will have a bar which is half 5 star, half Snickers, isn't it?
Yes, sir.
But unfortunately, this thing is not valid for semiconductors because there would be some problems due to the fact that these two surfaces are not perfectly plane and the imperfections are very much critical, very much crucial when it comes to making this kind of thing. I mean, if you just add randomly add two p and n type things together by hook or by crook, it won't form a junction. This portion is called the junction, where the two types of extrinsic semiconductors meet. Rather, what is done, first we take a intrinsic bar. Just take a plain, what should I say, chocobar kind of thing. So one portion you will be doing p-type doping. So one portion you're filled up with sugar. So this is p-type. Hmm. Another portion you would be suppose filling with hazelnuts or something. Is n-type. So that is how this kind of thing is done. If I get a video on this, I'll just share with you. But the video I saw is not very comprehensive. I mean, the real videos won't make much sense. Animations may help. So what happens when we do this thing? Let me redraw this. We have something called a junction. So this is the p side, this is the n side. This thing is called the junction. Now what happens to this thing? I mean, is that all? I mean, I'm keeping this thing, is nothing happening inside? Is it possible? I don't think so. So let us see what is inside a n-type semiconductor. What is happening on the n side? What kind of impurities we have? We have donor impurities, right? Why I'm making plus? These are the donor ions. Can anyone tell me why am I writing plus here? Any idea why am I writing plus thing?
Since
And
it's
either
donating, so it's
right.
adding.
Once you donate electrons, you become positively charged. So this side has this thing. See, I haven't come very close to the junction. It's like the no man's land. I'll explain why. Similarly, this side has accepted ions. Why accepted? They lack electrons and they can readily accept electrons. And these are the holes. That's the legend. This tells which symbol means what. You have studied this thing in your school as well, so I'll go very briefly. These things are near the junction as well. I'm not drawing it right now to be very evident. Fine. So once these two things are together, what will happen? P side lacks what? P side lacks electrons, isn't it? And inside lacks holes. Clear?
Yes, sure.
Right.
Yes. When I say lack, I'm talking in terms of the majority carriers. So this side have more holes, this side have less holes. So obviously there would be a tendency of these holes to move to the inside. Keep in mind, no external electric field has been applied, purely due to diffusion. Similarly, these electrons are seeing there are less electrons here. Why not move this way? Okay. Compare this thing with the situation of a battlefield. Fine. Yeah, these people are also trying to come here. So what happens? What happens at the junction? Can anyone imagine what happens near the junction? What will happen when electrons and holes are moving towards each other? What is likely to happen?
Chance of so like diffusion, sir.
No, diffusion is happening. That is why
Collision.
they are moving. Collision, right? What is the result of the collision? Who are colliding?
This should produce pulse, the electrons and
Electrons and
wait. So
electrons
you
and
said that
holes are,
like holes. So you said like holes don't move. No, so like just the electrons move. The holes just replace them, right? So
holes are just replacing them. Yeah, that is correct. But due to the motion of the electrons, holes are created. Okay, fine. No, no, holes do move. I said that they are not as free as the electrons. I mean, definitely they are moving, but you can't call them a true particle,
okay, sir. Okay, sir.
isn't it? Yeah, I can feel your confusion. There's a lot of confusion that sometimes we are feeling that holes are not true particles. I told this thing that the mobility of holes is less than that of electrons, but the mobility of holes is not zero. Okay, actually, holes are present in the valence band only. That is where holes can only stay. Now, the valence band is not always only holes. There are electrons as well, isn't it? If the electrons move, then only holes are created. Whereas in the conduction band, only electrons can reside. So conduction band is say uh, taken for granted. We can take for granted that conduction band is more spacious or more vacant than the valence band. So the electrons have a lot of freedom to move, but the valence band thing is much more stagnant and crowded. So since holes will have to stay here only, you can think that it is an overcrowded lane, and this lane is relatively less crowded. There is less traffic. So here the cars they can move, definitely they can move, but they don't have as much of mobility as the cars in this lane. So that's why holes have less mobility than electrons. Hmm.
Yes, sir. Got it.
Okay, now tell me what happens when a hole and an electron they will collide. I told last day with the analogy that
It
you
should
said.
produce
Yes, it will.
sparks. It should produce sparks or like electric. You're
Electric
like
spark.
colliding a negative part and a positive part.
What will happen then? If hole is nothing but a vacancy for electron, what happens if electron meets a vacancy?
It stays there, sir.
It goes towards
Yeah,
a recombination takes place.
very good. Recombination, exactly. So when a freely moving electron meets a hole, what will happen? They will recombine. That is what will be left behind is no, that is one electron hole pair is lost, isn't it? There is no more something called an electron and hole pair. So these things are more prominent at the junction, isn't it? Isn't it more prominent near the junction?
Yes, sir.
More collisions are, I mean, more things are likely to happen here.
Yes, sir.
Yes,
Isn't
sir.
it? Like you will see, there has been some, tragic incidents in sports history where there were disasters, where people were overrun in overcrowded stadiums. When the gate was tried to open, these people were the first to get trampled, isn't it? So what happens here? Near the junction, there would be more recombination compared to the interiors. So when a recombination happens, take this case, suppose this donor atom, here also I have a donor atom, undoubtedly, here also I have an acceptor atom. So this donor atom had a electron. A hole came and collided. So what will happen? Electron and holes will get lost. So what I will have only a donor atom. Similarly here near the junction, I had an acceptor atom with a hole. An electron came from this way. As a result, what left behind is a just an ion. So the portion of the region very close to the junction, it will have what? It will have, there should be another layer. Things. So see, a very small region around the junction, it will have what? This region will have only immobile impurity ions. More importantly, it doesn't have holes or electrons. Got it? Is it clear?
So they are after recombination, like they are immobile, no, sir. They can't move.
No. These things are already immobile. Atoms, ions, they are very heavy compared to electrons and holes. So when you apply an electric field or there is diffusion thing, these things are very less likely to be, as mobile as electrons. So these things are always, see inside here also, these things are always, fixed in their at their position. That's why we call them immobile.
Okay, sir.
So this region is very important here. No charge carriers, no free charge carriers can reside. They can't stay here. That's why this region is called the depletion region. Depletion means something lacking of something. Deplete means to lack, to have something in less number. So this region is depleted of free charges. So that's why this region is called what? This region is called the depletion region. It's very important how this region is formed. And see, again and again, I'm telling you, nothing has been applied from outside. No electric field has been applied from outside. This thing happened spontaneously. And after some point of time, what will happen? There will be, and this thing will occur only when there is equilibrium. Hmm. So once this depletion region has occurred, we'll see it in the next class. We don't have time today. So what you can see here, there are negative charges which can't move. Okay, this is still the p side. Okay, this entire thing is the p side. This entire thing is the inside still. So now what happens after the depletion region has formed? Suppose this electron wants to go, sorry, this hole wants to go to the inside. Why? Still there are more holes on this side than the inside. So see, it would be easily attracted by the negative charge here. It can easily reach the junction. Are you getting it? Let me zoom in. Yeah. So this hole wants to go to this side, even after the depletion region has formed. So it will be easily attracted by the negative charge. It will be attracted, it will reach the junction, right?
Yes, sir.
But what it sees on the other side of the junction, a positive charge. So what will happen? It will again repel it back. So this wall of positive charges, it will not allow any more holes to be diffused from the p to the inside. Let us see if the same happens with the electrons on the inside. So electron wants to go to the p side. It is attracted by the positive charge. Very good it here. Now it will again see a positive charge here, a wall of positive charges, a concrete wall. It will be again repelled back.
Negative charge, sir.
Right. Sorry, negative charge. So you will see thus equilibrium has been achieved. That is, equilibrium means what? No more majority carriers can break the junction and move to the trespass. Trespassing has been checked. Okay. Clear?
Yes, sir.
Because due to thermal energy, all the charge carriers are energetic and they may have some energy to reach the junction at any point of time. Now one thing we ignored, the side roles we ignored. I'll just quickly tell in 1 minute. Okay, we're already out of time. Inside have minority carriers. What? Inside have very less number of holes. Remember minority and majority carriers? Remember this?
Yes, sir.
And p side has very less number of electrons, minority carriers. Suppose if majority carriers are, say, 1 million in population, say minority carriers are very less, say 10 to the power 5 times lesser. The good thing for the minority carriers is that, see, the electron, it can't reach here. Why? Because negative charge. But due to thermal energy, there is always a probability that this electron gains sufficient energy to reach the junction. Okay, because it's a random thing, it's a statistical thing. We don't know exactly which electron has what amount of energy. It can have anything. Suppose it has so much energy that it can somehow reach the junction. Okay, from there what will happen? Easily it will be attracted by the positive charges on the other way and it can move this way. This is for the minority carriers only. You're getting it?
Like after getting, sir, enough energy, sir. Like for
Yeah,
thermal
I
agitation.
mean they have to have the energy to reach the junction. which is a bit difficult. Why? Because electron has to overcome this negative charge barrier on its p side only. Similarly, if by chance some hole gets sufficient energy to reach the junction, it would be easily attracted here and it would be drifted this way. So the important take home message is that majority carriers are diffused, and minority carriers, they are not moving due to diffusion, mind it. Here there are more holes than this side. Why should it move that way? It is being attracted by that, so that is, it is being drifted. And this thing is very, you can see, if out of 10, if two electrons are moving that way, it will constitute very, very less amount of current. Fine. So this amount of current doesn't, give us any important thing. I mean, it doesn't have some practical utility. Is it clear?
Yes, sir.
Did you see a news very recently when I think nearly 1 year or 2 years back, not very recent, the news came recently that a officer or a person from North Korea, he somehow managed to, come to the border and then he could go to South Korea. Did you see that news? There's a video.
No, sir. But I'll sort, sir.
I think you all know about North Korea. What is the life of people in North Korea
Yes, sir.
compared to
Military
South
rule, sir.
Korea? Yeah, that one person's name is enough. So what happened there? I think a police personnel, maybe he just stole the one, not stole. He just took a police car or that army police car, maybe. He somehow reached the border, and the border is very heavily protected in North Korea. They don't want anyone to go to South Korea. So what happened? He had to leave the car. They already started fighting. He was heavily
It's a
injured.
border of
Border,
South Korea, no?
right, border. So somehow he could manage to reach the border, and from there the South Korean that
Yes, sir.
security
With the
force,
yes, sir.
they could, yeah, take him back. So same is with the minority carriers. If you are courageous enough to reach the junction, then you would be, rest is taken care of. So here the courage is not about courage. Here it is about having sufficient energy, which is purely statistical, probabilistic. Okay. So next class we will just see what happens to the electric field and potential thing in this region. Okay. So that would be on Monday, I think.
Yes, sir.
Is it clear? Any doubt from anyone?
No, sir.
No,
Thank you,
sir.
sir.
Okay, thank you. Best of luck with your elections.
Okay, sir.
Okay.
Thank you,
Thank you,
sir.
sir.